Hello, buenas tardes. So I'm going to start speaking in Spanish, Michael, to the audience, okay?
Muy bien.
Okay. Bueno, buenas tardes, bienvenidos a esta nueva actividad. Tenemos en este espacio a Michael Bolton, que es un consultor y profesor de pruebas de software. También es coautor de la metodología Rapid Software Testing, con más de 30 años de experiencia en testing y desarrollo, y ha enseñado este tema del RST en más de 35 países y lidera la consultora DevelopSense. Bueno, Michael es oriundo de Toronto, Canadá. Bienvenidos a todos. Les pido que a medida que vayan teniendo preguntas las vayan escribiendo en el chat, así se las podemos luego hacer esas preguntas a Michael. So now I'm going to switch to English. Hello, Michael.
Hello.
Thank you so much for being here with us today. Glad to have you on board. So the audience is eager to know about the difference between demonstration, experiment, and testing, right? Now the stage is all yours. You can start your presentation. Thank you so much.
Well, thank you very much, Lucia. And I apologize in advance if I start coughing. I've been traveling, and you pick up all sorts of wonderful things when you go traveling, including souvenirs of the experience. And I do want to, let's see, I have to connect my YouTube account to join the chat. Maybe I wish we didn't have to do that. But maybe, Lucia, if you can help me by interrupting me when you see people with questions that they'd like answered. Yes, today we're going to talk about demonstration and experiment and software testing, and how testing is really at its core science applied to investigations and understanding of software products and services. So let's look into that. Once upon a time, there was this thing that looked like this. I don't know how many people are familiar with it, but what this is the most sophisticated and advanced scientific instrument of its day. Around the time, the year 1600, 1660, 1661, in the 1600s, at the birth of the approach that we now know as the scientific method. This is an air pump. It was designed by a couple of fellows, Robert Boyle and Robert Hooke, who were very interested in performing investigations on the air. In particular, one of their mentors and one of their predecessors, a fellow named William Harvey, had discovered that the blood in the human body circulates. It goes all the way around the body, and something interesting happens when it passes by the lungs. It goes from blue to red. And these early scientists were interested in what that might be about, and they suspected that it might have something to do with air, what we breathe into the lungs. Now, what I'm going to tell you about over the next little while is it starts with a book called Leviathan and the Air Pump. And it's an account of how Robert Boyle and Robert Hooke and a bunch of their followers got into a great big fight in the 1660s and around that time with a fellow named Thomas Hobbes, over what constituted what science should be about. And that argument and that discussion is really fundamental, I think, to the way we might think about how testing works out. Now, the source material for this is that book, but also a really terrific radio series called How to Think About Science, of which a discussion of the ideas in this book form the first episode. There's 24 episodes in the How to Think About Science series, and this one, this set of ideas involves the first one, but it goes all the way through that series. And if you're seriously interested in testing, this is a very worthwhile series to listen to, in my opinion. So Boyle and his followers had some ideas about how to perform what they called experimental philosophy, what we now call science, or the scientific method. The ideas went something like this. Number one, we work with instruments and machines to perform experiments in which we, in some senses, distort or change the usual course of things, the normal course of things. One of the things that they figured out about air was, if you want to understand the properties of something, it might be a really good idea to get rid of it. And it reminds me of something that we used to do at my company in the 1990s, a company called Quarterdeck. When we wanted to investigate the effect that a certain file or that a certain module had on a system, one of the things that we would do is we would rename it, delete it, make it unavailable to the product that it was a part of, and see what effect that had. Another thing that Boyle and his followers thought that we ought to do in order to learn things about stuff was to bring people together to witness a demonstration of what had been found during the experiments, and then to publish or to document the experiment in the form of a story, an account. The idea being to bring people in to the experiment so that they could come to agree on the conclusions of what the experiment purported to help us learn, purported to help us tell us about. And then to also produce plans and procedures so that if you wanted to perform the experiment yourself and see the same effects that they had seen, you could do that. And so as part of their approach to doing all this, they produced plans for this very sophisticated, very advanced instrument, the air pump. Now, the way it worked was there was a glass a sphere at the top, and then there was a valve by which you could let the air back in, but you could also turn it out. And then there was a crank here by which you could pump the air out of the sphere, and notice what effect that had on things that were inside it. So you could put stuff on the inside, like a candle, and pump the air out, and then you could see the candle going out. Or you could put a mouse on the inside and pump the air out and watch. After a minute or two, the mouse would start struggling and gasping for breath. And then after a couple of minutes, the mouse would really start struggling. And after 2 or 3 minutes, the mouse would lose consciousness. And if you kept it in there for long enough, it would die. So once again, helping to try to figure out the relationship between the air and living things. Or if you put 2 polished pieces of marble, little discs of marble together that stuck together in normal atmospheric pressure, when you pump the air out, these things would fall apart inside. They would come apart on the inside of the air pump. Now, of course, they didn't have rubber, and they didn't have particularly sophisticated ways of sealing this. So that led to some issues and some problems that were objected to, brought up by a fellow named Thomas Hobbes. Now, Hobbes simply didn't believe the approach, didn't believe in the approach that Boyle and the early scientists were following. And he had a number of objections to the approaches that they were taking. Now, first of all, he said, the machines don't actually work very well. They don't create a vacuum. this was Hobbes's belief, was that, if you thought they created a vacuum, well, they all leaked. Now, how is this similar to our world of testing today? Well, there's a common problem with tools that they can't deal with stuff that's common in terms of showing what they appear to represent. Notice that focusing on repeated output checks, trying to perform an experiment, it doesn't deal very well with things like how the browser window is sized or resized. Stuff that happens inside the browser window where stuff disappears and reappears. The timing of the appearance of elements. A lot of the tools that we're using, especially for automated GUI checking, are fundamentally unreliable in the same kinds of ways that the air pumps were reliable back then. It's true today. It was true 25 years ago. Many of the tools that we've got these days simply don't work very well, just as Hobbes was pointing out that the tools that these scientists were using for their experiments didn't work very well in those days. Now, I was using a tool called SAMI, and not very long after that, another tool called Water, and those ideas went into another tool called Selenium. These are not new problems. Notice from 2005, back in those days, they were still dealing with problems of timing and things appearing in the browser window and waiting for documents to be finished uploading and so on. And notice that there were tools even back then that would help you to write automation scripts. Well, hello, we're still in the day where Playwright purportedly helps us to write scripts. And yet sometimes when we encounter things like iframes, Playwright loses its capacity to do that. So these are not new problems. So that was one of the objections that Hobbes had, and it's very similar to what goes on in testing today. The tools didn't work very well. Another problem that Hobbes objected to in this scientific method was that experiments were based on your theories about what was true. And that what the scientists were doing, Hobbes said, was they were simply doing things that were consistent with what they believed in, their theories. Again, Hobbes did not believe in the vacuum. He didn't believe in what Hobbes and Boyle referred to as the spring of the air, this tendency of the air to be kind of elastic and so on and so forth. So here's another way of looking at that in the current world, in the world of testing. Here's a test, people say. We verify that the user can log into the system by providing an email address and a password, and then showing that everything's all right once they log in. But what's our notion of everything? Theory says yes, that if the user can log in and we don't get any error messages, or if we get a simple message that says that the user logged in successfully, well, here's what I think about when I'm looking at a login issue. I think about the risk that somebody who's authorized to log in won't be able to do it. Maybe because they forgot their name, they forgot their password, they forgot both. Maybe they're a new user and they're not yet authorized to log in. Or maybe the user won't have access to resources that the user should have access to after logging in. Or maybe the user will have access to resources that they shouldn't have access to after they log in. Maybe unauthorized users will be able to log in. Hackers will be able to do it via brute force or by some identifiable vulnerability. Or maybe a hacker will be able to evade the login process and get in and do all kinds of nasty stuff without ever having logged in at all. Or maybe there's some kind of vulnerability to the system that you can exploit. Maybe the login fields will be vulnerable to known kinds of security problems, or maybe the error message will reveal too much to hackers. So there's all these different kinds of things to consider quality criteria associated with the experience of a login process. Is the login process capable of what it's doing? Is it reliable? Is it usable? Is it secure? Is it friendly? Is it easy to use? Does it look good? All of these different aspects of things are things that I would think we would need to consider during the process of examining a login process. So the theory that says, hey, once we've successfully got the login prompt, then everything's going to be okay. Well, that's, I would argue, not enough to declare that the product is problem-free or trouble-free. These are the ideas that I brainstormed after an hour of not really investigating too much, not really thinking too hard. This is a space that I think a good login test has to cover, rather than a simple check for is the thing successful using one very limited oracle, only one way of recognizing a problem. Then there's a notion of reliability. When we perform a test, what we're trying to figure out is something that's not necessarily available on a one-off, on a single instance of showing that the product can work. Hobbes objected to Boyle and Hooke's experiments and those kinds of processes, because he said, well, just because something happens in one place at one time doesn't mean it's always going to happen every place, every time. Seeing something happen once isn't enough, said Hobbes. Just because it happens in a studio or a drawing room, a salon somewhere in central London doesn't mean that it's going to happen the same way at the top of a mountain. And just because it happened today, it doesn't mean it's going to happen the next day reliably. So this leads to two kinds of ideas about reliability and validity in qualitative research. And this particular book, very slim, thin little book, is a really, really wonderful supplement, basis for thinking about the way we think about testing. I would argue that testing is indeed a form of qualitative research about the product. So let's look at what scientists think about the validity and the reliability of observation and experiment in science. Three kinds of reliability. These are big words and they're kind of fancy, but they amount to this. Observations that we make in the same time period should be consistent with each other based on, well, what's true here on a Chrome browser on the same day should be consistent with what's true here on a Firefox browser or on some other platform or on a mobile platform. Then diachronic reliability. That's the basic idea that if we make an observation today, then one of the ways we have of suggesting that it's a reliable observation, if we can make the same kind of observation tomorrow. What was true then is true now. But there's another kind of reliability that can fool us. And that comes from Don Quixote, a very famous Spanish language book originally, that we can be fooled by the idea that when we see something that works the same way and over the same time, that we get a consistent and supposedly reliable observation. But here's the trouble. We can have a consistent, reliable observation of what the temperature is today and tomorrow and so on and so forth. But just because it's consistent and reliable doesn't mean that it's right. That is not, I hope, the temperature anywhere on Earth. Otherwise, it's going to be kind of warm. So in software testing, once again, same kind of idea applies. A broken thermometer is similar to a check that ran green yesterday and still runs green today. It does that not because the product is okay, but because there's something wrong with the check or there's something wrong with the environment. One of the problems we run into is we tend to pay attention when checks run red. We don't tend to pay so much attention when checks run green. Why would we be so sure that the product runs okay just because a check that ran green yesterday also runs green today? Maybe we're being fooled by green. Maybe it's entirely possible that green can fool us. Now, how might green fool us? A green check can fool us in any number of ways. I'm going to pop to a slightly a different presentation. It occurs to me that I've got this in some other form. So I'm going to pop over to that just for a sec. When we're performing some kind of test where we're performing a regression test, one thing that a check might tell us, an automated check, is that we've got either a problem or no problem. So we run a test based on an automated check, and we see a problem. Well, that could be false. That could be false because the test process might detect a problem, but it turns out that the problem is actually what the check says as a problem is actually a false alarm. The test process might detect a problem and it's a real bug. So if our evaluation of the test is that it's true, then it's great. We found a real bug. Yay. But the green can fool us. The green can fool us and mislead us because the test process might be inadequate or broken in some way such that it doesn't reveal a problem that actually does exist. Now, of course, if it runs green and there is in fact no problem, and that's true, then that's great. The process doesn't reveal a problem because the product is actually fine. But what we got to be careful about is that green can mislead or harm us in various kinds of ways. A demonstration that something is okay is not a test. The check that ran green might not really be a check at all, but something that simply reports a happy outcome by default without ever performing any kind of process. A check that was a real check might not have actually been performed even though we thought it was. The check might be performed, but it might switch by accident the output. The output should have said red, but actually it said green and vice versa. If we checked using a different process, then the check's procedure might be controversial. It might check the same explicit factor using a different routine and produce a red result. Well, look, here's an example of that right here and now. I've got in this presentation something that is appearing out of order. What do you know? In fact, oh, here it is. Look at that. There we go. The check might produce output. The check might check output, but not to the degree of precision necessary to check whether the product is indeed producing sufficiently precise output, or vice versa. The check might be too fussy, suggesting that the product is wrong. This is when we get a red check. And when the product is actually just fine and the check is too precise. Some people might disagree on how to interpret the check. The checks might address some kind of quality criterion that we don't actually care about. So the green check can be irrelevant to what matters to us. The check might cover too few samples from a big domain of space in which we could be checking the output. Maybe the variation in the timing of the check would make a green check run red if we vary the timing just a little bit. Maybe there were too few conditions that were getting checked and too narrow a way. Maybe the check was wasteful or unnecessary or redundant or obsessive compulsive. and we don't actually need that check, and it's just wasting time on us. Maybe the product has changed since the check was performed. So we ran the check a little while ago, the product has changed since then, and the green check that ran earlier is going to fool us into believing that the product is okay. Maybe we log a green before the check is actually finished. And this is a real problem for us theory testers. This next thing, we don't know what the checks actually do. So we don't have a basis for making a responsible judgment about them. Dear testers, never run a check that you don't understand, with one exception. One exception. The exception in which it makes sense to run a check you don't understand is run that check if your goal is to understand what the check does. But if you're running a check that doesn't understand, that you don't understand, that you don't know the internals of it, you don't know how it works, you have no basis for deciding that the product is okay based on seeing a green. And another thing that crops up, supposing we have a suite of 100,000 checks that we run every day. How often is it that we review those checks, that we try to look at those checks to see if they're actually valid? If there's 100,000 checks, where there's 250 working days in a year, in order for each of those checks to get examined once a year, just once a year, we would need to review 400 checks a day. So if there's a sufficiently large body of automated checks is incomprehensible. We can't understand what they're doing well enough for them to provide a reliable guide to just how good they are. All right. Another reason to be suspicious of demonstrations, which is what automated checks actually represent, is that when you perform a check, the outcome might be controversial. You know, you could say that people having seen a demonstration, they'll automatically agree that everything's okay. That if you see a demonstration that a check that runs red represents a problem, that everybody will conclude, oh my goodness, well, there must be a problem in the product. But no, first of all, no responsible tester ever reports immediately that the outcome of a red check indicates that there's a problem in the product. We don't do that. We have to investigate and analyze the output of the check. We have to analyze the procedure. We have to analyze what the check actually meant. We have to interpret the results and evaluate them and investigate them. And you know this as a tester. As a tester, you know this because have you ever reported a bug and been challenged by the developer? Automated checks should not form a basis of an agreement that everything is fundamentally okay in the product, nor should a red check automatically suggest to us that there's something wrong with the product. There could be something wrong with the check. This gets to the core of demonstration versus experiment. The essence of science is not to demonstrate that our theories are correct. The essence of science is to challenge our beliefs. And let's look at that in some detail now. In a demonstration, the idea behind a demonstration is to show what we know, to show that what we know to be true, what we believe to be true, what we hope to be true is in fact true. For an experiment, that's not the case. For an experiment, the idea is to challenge what we think we know. That's, I think, what we need to be doing in testing, not to demonstrate that everything's okay, but to challenge our beliefs about what's okay. A demonstration to be successful and smooth often requires a lot of rehearsal. But the nice thing about an experiment is an experiment can reveal a problem, a challenge to our beliefs about what we know in a single shot at it. We don't need to polish the experiment in order to reveal that something that we thought to be true about the product might not be true. In a demonstration, if we do it over and over and over again, that shows in a desirable kind of way that we're getting consistent behavior. But consistent behavior in a demonstration isn't the goal of a test, of an experiment. Reproducibility rather than repetition can reveal interesting inconsistencies. That's what we want to expose. We want to find out when the product is behaving differently in different circumstances, using different data, using different inputs, using different sequences. We want to see when the product is behaving in different ways. Inconsistency in a demonstration is undesired, and it's troubling, and it's something that tends to make people uncomfortable. That's true, but the essence of testing is not to reassure. The essence of testing is not to build confidence. The essence of testing is to show when confidence is unwarranted. So when we see an inconsistent result in a test, that's good. That's useful information. That helps us to recognize that there's something about our sets of beliefs about the product and about the check, or about the environment in which we're running it, or the timing in which we're doing it. We want to know about anything that would reveal some kind of misunderstanding there. Now, maybe the product is perfectly fine and the checks are inconsistent because of errors in the check. Well, if that's true, we want to address that by addressing the checks so that they reveal what we really want them to reveal. If it's true that there's that the check is okay and there's a problem in the product, we want to know that. So inconsistency is something a lot of people get upset about. They talk about flaky tests. But I don't think there's such a thing as flaky tests. What there is tests that aren't finished yet. If we're seeing an inconsistency in a test result, that is important information. It reveals that there's something that we don't know that would be a really good idea for us to know about. Something in our models of the product space and the test space that requires us, I would argue, to look into it. In a demonstration, when we vary the factors, when we vary the input, or when we vary the sequences, that's risky. It gets in the way of the demonstration going smoothly. But for an experiment, in a test, we want to vary the factors. We want to vary the conditions. We want to vary the sequences. We want to vary the platforms and all the other elements of the test, because it may improve the experiment by helping to reveal something that we didn't know before. In a demonstration, what we're really trying to do is we're trying to put a lid on risk. If there are problems, a demonstration won't reveal them. It's a nice, smooth, happy outcome, and nobody gets upset, and the developers don't say, oh my God, we've got to address this problem. The project managers don't get upset. We don't have to deal with threats to the schedule or threats to the value of the product. But in fact, the whole purpose of testing is to investigate risk, to identify risk, and to find out where there might be problems that threaten the value of the product. Now, that's not always happy news, but in the long run, it seems to me it's important to know if there are problems in the product. That is the first space, the first step in addressing those problems and making products better. In a demonstration, deeper truths are kind of beside the point. But in an experiment, in a real test, deeper truths are the goal. That's why we're doing the test in the first place. Now, that leads to us a distinction between testing and checking. Why do we talk about testing and checking in rapid software testing so much? It's because the easy part of a test is the part where we're checking the machinery for problems in functions and problems in logic. So the idea there is that computers and their software are actually two things. They're, in one sense, this is comes to us from a fellow named Harry Collins, by the way, who made these statements part of his abstract for a talk that he was to give at Eurostar 2013. And it just strikes me as a beautiful way of looking at this. Harry Collins is a sociologist of science, and this is his point, that testing and science are both things that require social competence, a social evaluation, in order to reveal things that we want to know about. We'll return to that point in just a sec. But Harry points out that computers and their software are machinery, and we have to check the machinery to make sure that the machinery is operating properly. Okay. But he also points out that machines, software, fit into human life where people used to fit, or people with certain superpowers could fit. And the issue there is that whenever we have a medical prosthesis, like an artificial heart or an artificial pancreas, like an insulin pump, they don't do exactly the same thing that a natural human body part would do. And the human who uses this prosthesis has to make a decision about whether they're happy enough with it and whether they're willing to compensate for the difference between the prosthesis and the human body part. Now, Harry's point is that computers don't do the same things as humans do. So in that sense, they're like an artificial heart or like an artificial insulin pump or like an artificial arm. They don't fit into society the way humans do. And so the society in which the software is being placed has to make some decisions about whether the software is good enough to deal with the difference between what software does and what people would do. That means that as testers, we can't just be checking the output. We can't be making sure that the cable on the artificial arm makes us able to stretch and pick up something in the hook. I say this because my brother had a prosthesis. My brother has no arm from here down. And he had that kind of arrangement. He had a thing that would pick up this stuff. And then if you expand your shoulders again, then the hook opens up and it drops the thing. Well, he decided, my brother did, that having a prosthesis just wasn't for him because it didn't sufficiently address his needs as a person who has a hand and a stump. He could deal with that well enough, and the artificial prosthesis just didn't do the job that he needed it to do. So as somebody who's testing this, sure, we could check to make sure that the machinery works, but we need something more than that. We need to decide, and as testers, we need to help our clients decide whether humans are going to say this is good enough, not just whether the machinery works right. Harry talks about why democracies need science in a book, basically, that has that title, that has that name. And in that book, he makes the point that democracies need science because what we need is to look at the truth of how things work, both from a physical sciences perspective, but also from a social science point of view. We need that, and we need people to actually observe and interact with our products because we want people to engage with those products and observe them as people are actually going to see them. And Harry raises the point that in society, if you want to know about something that is a feature of the world, who do we prefer to listen to? Somebody who has actually looked at the way the world works, like a good sociologist does, like a good anthropologist does, like a chemist does. Or would we rather trust somebody who says, well, I'm not a scientist, but I bet ivermectin is a good cure for COVID? Well, we want somebody who's actually performed the experiments and performed the observation, collected the data, even though we know that human observation is imperfect and it's open to illusions and observer effects. It's open to the influence of social groups, but we prefer to have a social evaluation of whether that person has actually looked at the thing or is just theorizing about it. This brings us to something kind of important about the way we think about testing. Testing, in order to be successful, needs to be to some degree interactive. It is silly and unhelpful, we would argue, to talk about manual testing and automated testing. Testing can't be automated. Anything that we call an automated test is something where automation is performing some part of the testing activity, but the essential parts of the testing activity are the bits where we design the experiment, where we think critically about risk in order to design the experiment, where we encode the experiment in a way that allows people to exercise the product, and then some automation can happen at that point. But after the automation has done its thing in a way that's maybe unattended or not interactive, we need to once again look at the outcome of what's happened and evaluate that, interpret it, analyze it, and understand what has happened in the course of the automated activity. It's not in any way a good thing, I would say, just to simply say, well, because an automated process turned a light on that turned green, that's not going to tell us what we need to know in a test. This is why we make the distinction between testing and checking in rapid software testing, because the check is only part of the test. It's the part of the test that's embedded inside a testing process. It's the part of a test that can be automated, that can be unattended. But in order for it to be a test, we need to have human involvement before the check and human involvement after it to make sense of what the check is doing and make sense of what the automation is doing. Similarly, for testing to be successful, we've got to look at the product from the point of view of people experiencing the product, not necessarily just the end users of the product, but in the case of, let's say, an API, the people who actually use that API to try to get things done. So again, another circumstance in which we don't want to rely simply on a check that confirms that we can make a call to an API and get a 200 back and maybe get a JSON that shows up in a certain specific form. We need to analyze the data that comes back in that JSON and to see that if it fits with how the programmer is going to use that information and convey it to the end user. We need to look at the documentation for the API, and we need to ask, does that documentation help the programmer who is going to go through the experience of trying to build something with that API? Does that API help the programmer who is going to interact with it in terms of some person who is interacting with the product on an experiential basis? So let's remember that an API does have a human user, and that human user is the programmer. My recommendation is, if we're going to test an API, we've got to test it not only from the perspective of checking the output that comes back from it, but from what it's like to build something using that API. And another reason we would say not to say manual testing is to use something more specific and talk about the circumstances in which we don't have a procedure that has a very detailed or very specific procedure in mind, but one where the tester is engaged and able to exercise agency about what choices were being made through the course of performing the test. So dear testers, please, let's not talk about manual testing and automated testing. It's normal to use tools any part of the testing process. Nobody talks about manual researchers and automated researchers. Nobody talks about manual journalists and automated journalists. Let's avoid doing that. Now, automated checks can help us sometimes, and tests that we repeat can help us sometimes to corroborate certain things that we thought or hoped to be true are still true. Now, we want to make it possible for us to provide an account of the testing that we've done, to be able to reproduce the circumstances of the test. So we can say, we did this test yesterday, we can do a similar test today and corroborate that what we did yesterday can be replicated in some kind of way, that it can be reproduced. That's a fine thing. But then we've got to worry about the fact that sometimes we get pushback when somebody says, oh, you're not getting the same result today because you didn't do the test right. We've got to be careful about repetition, because it can fool us. Repetition can fool us into believing that just because we saw something work yesterday, or we saw something work 10 times in a row, that means it works. What it works really means is it appears to meet some requirement to some degree. After all, we can perform a test 10 times, 11 times, where what we're testing is, does x plus y equal 10? Well, imagine a routine in which x starts at 0 and y starts at 10, and on each iteration through a loop, x is incremented and y is decremented, and each time we go through, let's see, x equals 0, y equals 10, x plus y equals 10. Yep. And then we go through the loop again. X equals 1, y equals 9. Yep, x plus y equals 10. And we can keep doing that until x equals 10 and y equals 0. We've done that. At that point, we've done that test 11 times. But on the 12th time, there could be a circumstance in which, yep, y stays at its floor of 0. But the developer has forgotten to include a check that caps x at 10. And so x suddenly equals 11, y equals 0, x plus y no longer equals 10, it equals 11. So remember that there's a big difference between can work and does work. There's a big difference between does work and will work, because we can corroborate that something seems to work, that it appears to work. And we can infer that if it worked this time, maybe it'll probably work the next time. It'll probably be true the next time. But until we've examined every possible state of the system, including states that we're aware of and all the states that we're not even aware of, that we don't even know that we're not aware of, we can't verify ever that x plus y will certainly be true. So corroboration is one thing. We've got to pay attention to falsification as well. Here's why. This comes again from Kirk and Miller's book. They say most of the technology of confirmatory and non-qualitative research, that is to say, like in testing, that'd be kind of like output checking. Most of that is aimed at preventing discovery. When a confirmation or a demonstration goes smoothly, everything comes out as expected and nobody has to worry about stuff. Everything's smooth. And our theories that everything's okay, that's supported by just one more example that everything seems to be okay and nobody has to worry about anything. But the trouble with that is that confirmation and corroboration is kind of the absence of any kind of insight. If we're going to show that everything's okay, well, that's all right to some degree. But really, a problem in the product or a problem in the check almost by definition has to be accidental. Somebody has to have made a mistake someplace. So what we want to see, once again, is that true dilemma being resolved and being addressed by the fact that we can be fooled by that. What we really want to see, it seems to me, is falsification. What kind of a world do we want? One in which the observations that we've made can be actively shown to be wrong, where we actively invite the test. That's what Harry says about Harry Collins and Robert Evans say in Why Democracies Need Science. Do we want to have a world in which we're willing to set up circumstances in which we can falsify our beliefs about what's right and what's wrong? Or would we prefer to have something where that's going to get suppressed, where that's unnecessary or inappropriate? Notice that they're actually using the words invite the test in this book that's about why democracies need science. That's a formative aspect of science. I would argue that it's a formative aspect of testing as well. We've got to set out circumstances in which we're actually going to invite our beliefs about the product, about the system, about the thing that we're trying to create for our end users. We want to set up circumstances where we can find out that that stuff is wrong. And we want to find out where it's wrong because what we want to try to do in testing is to get rid of damaging, incorrect beliefs about the quality of the product. That's what we're doing. What we're doing is we're trying to go from assumptions about the goodness of a product to evidence about it. We want to go from an assumption that the product is okay, that everything's good, to stronger beliefs about the product such that we could collect enough evidence in order to suggest that our beliefs about the product are more like facts. So a fact is something that we believe is true, that we treat as true based on the fact that we've got sufficient evidence, we can make reliable inferences to believe that it's true. Like this. Testing is a process of evaluating the product by learning about it through experiencing, exploring, and experimenting. So one way to think about what we're doing in testing is we're collecting premises, starting assumptions and starting facts about our beliefs about the product. We're checking safe assumptions about the product. That is to say, we're looking at those things and not looking at them too deeply. We're questioning risky assumptions. That is, assumptions where the facts could be in dispute, whether our evidence is weak. And we're gathering evidence to expose weak inferences. And what we're fundamentally doing in testing is that we're challenging assumptions or hypotheses that others believe to be facts about the goodness of the product. Now, a key difference between testers and other people is that we're challenging products that a lot of other, we're challenging assumptions that everybody else believes to be safe. So, what is a test? What is a test? To a developer, or to a designer, or to a manager, a test might be a checkable example, or a checklist item to be accomplished, a ticket to be looked at in Jira. It could be an obstacle to be overcome, a hurdle to be cleared, something that we got to see that the product is doing this to say that we've done something successfully. A test might be limited to a simple demonstration, but that's why in rapid software testing, at least, we want to make that clear that that might only live up to the point of operating a product algorithmically to check specific facts about it, as though a spelling checker were what people would consider to be editing. Well, with a spelling checker, what we're doing is we're not actually editing, we're just collecting some facts about words, tokens in a documentation, making sure they're in a dictionary someplace. But nobody calls spelling checking automated editing. To us, in rapid software testing, a check is part of a test a lot of the time, maybe sometimes. Even a large number of checks are part of a test sometimes. partially. But for us, a test is way more than that. Testing for us is evaluating a product by learning about it through experiencing, exploring, and experimenting. And that includes questioning the product, studying it, making mental models of it, making some explicit models of it in diagrams and flowcharts. It's operating the product. It's interacting with it. It's analyzing risk. It's thinking critically about it. It's designing and performing experiments by which we can learn about the product. And that means, as well, creating the conditions necessary to do that. And also acquiring the skill and the reputation and the desire to create the conditions necessary to evaluate the product by learning about it through experiencing and exploring and experimenting, so that our clients can make informed decisions about risks, problems in the product. That can help make the product better, but testing alone doesn't make the product better. In testing, we don't prevent problems. What we prevent is oblivion to problems. We can help people make the product better by helping them understand problems that exist in the product so that they aren't fooled by false beliefs about the state of the product. So, in testing, to go back to the unreliability of our tools, we're mostly working with tools built by other people. Sometimes we craft our own tools, but the trustworthiness of our work is dependent on how much we trust the tools and the makers of those tools. A lot of the tools that we're using especially in GUI automation and now in the days of using large language models and generative AI in order to help us test, these tools have lots of problems and lots of bugs. Find testers who are willing to examine those things and who are willing to tell the truth about them. Our mission as testers is not the mission that the builders have. We're here to help the builders by understanding the product and threats to its value through experimentation. And that's got to be different from the mindset of the builders. It's our job to get to the truth of the product, not to show that everything is okay. Apparent reliability is very seductive. Discovery is disruptive. Be prepared for the politics and the pushback associated with that. There's social forces for testers that we have to deal with that are going to cause us to be reluctant sometimes to draw attention to problems. But the fundamental mission of testing, I would argue, is to find problems in the product so that the people who matter can deal with them, can attend to them, can take action on them. And then finally, science is the core of testing, not marketing, not reassurance. And that is why we've got to focus on experimentation and not just demonstration as we go about our work. There you go. I'm happy to take any questions that we have time for and that you might have. If it turns out that we don't have time for questions, I would also welcome questions and feedback via email. You can reach me on LinkedIn. There's any number of ways that I can be reached. And if you're a good tester, you can figure those out. But until then, thank you very much. Martin says,
thank you,
I agree.
Michael.
Thank you.
Hi, thank you so much. Unfortunately, we are running out of time. So as you said, they are going to send you the questions. And really very nice presentation. Thank you so much for sharing with us your expertise.
And thank you for hosting me. It's been, I hope to visit Chile and maybe Uruguay, Argentina. I hope to visit.
Yes,
Well,
please,
all
come
you have to
here.
do is ask. And if we can work together on setting something up, I would absolutely love to visit South America again.
It will be our pleasure to have you here, Michael. Thank you so
let's
much.
stay in touch then. Thank you.
Have a nice one.
Thank you.
Adios.
Gracias a todos.